We are still working on solving equations. Still getting comfortable with our unit circle. We're just going to take it up a notch with the types of equations. So far we've been dealing with some of your more basic equations, just getting comfortable with our unit circle. This type of equation is still pretty basic, but you should notice that there's a difference between this equation and some of the other equations. And that is the fact that there's a 2x in the parentheses instead of a regular x. When that happens, what that means is that you're going to have to adjust the domain in which your x lies, because as you can see, these do not match. The domain is with respect to x, but inside of your parentheses, you have a 2x. So anytime your variable is not just a variable by itself, but has other things in it, you have to adjust your main to compensate for the fact that, like in this case, it's being doubled. So because x is being doubled, that essentially means I need to multiply both bounds by 2. So then that way it can be with respect to 2x versus just regular x. Does that make sense?
So it's like 0 and 17.
Right. So by multiplying both bounds by 2x in this case, because again, we're doubling x. Now, when I ask myself, where does sine equal the square root 2 over 2, I'm not just looking from 0 to 360, I'm looking from 0 to 720, because I'm trying to make sure I include all of the values that work. So square root 2 over 2, a positive square root 2 over 2 occurs in which quadrants?
The diagonal right, like bottom left.
Where it's positive, where sine's positive.
The top quadrants.
The top quadrants, yep. Because remember, sine is which coordinate?
The y coordinate.
So you're looking where sine is positive, so that's going to only happen in the first and the second quadrant. Root 2 over 2 is which angles? And we're in degree. So
45.
From 45.
And 135.
And 135. Okay, so from 0 to 360, those are the only two angles where sine is a positive square root 2 over 2. But I'm going until 720 because I had to adjust my domain. So I have to go around one more time to compensate for the fact that I'm going all the way up to 720. So I've gone around for 360. Now I need this angle after I've gone a full 360 degrees and I'm back at 45.
405.
So that's 405. And then keep going until I get to 135.
495.
And remember, we're just getting these by taking 360 and adding 135 and 360 and adding 45 to get the other angles. And then that'll cover me until 270. So where sine is a square root 2 over 2 from 0 to 720, it's 45 degrees, 135 degrees, 405 degrees, and 495 degrees. But those aren't my full final answers. Because remember, when I took the sine inverse, this was still equal to 2x. So that means that all of these solutions need to be equal to 2x, and then I need to solve for x. So that means I have to divide every single one of these by 2 to actually get my final answers for x.
Well, you want to make it into a decimal?
Yes.
Okay.
So what's half of 45?
I'm not good at that.
Wait, 20.
What's half of 44?
Is it 22.5?
It's 22.5. So you take half of 44 and then you add a 0.5. What's half of 135?
135, let's see. 150, 30, 50. So would it be 45.5?
No. How many times does 2 go into 13?
I mean 65, sorry, 65.5.
Not 65.5.
Okay, now I'm done.
How How many times is 2 going 13?
Wait, I know that.
7.
So then it is 67.5.
My bad.
All right, what's half of 405?
202.5.
And what's half of 495?
247 plus 23.
And then these are all of your angles. Every single one of these, if you notice, lie in between 0 and 360. So that still holds true, but we had to, again, adjust our domain to make sure that we included all the possible values that when we plug them back in for X, will give us a sign that is sine of 2x that will essentially equal the square root 2/2.
Question.
Yes.
So when we change the 0 and 360 to 0 and 720,
Mhm.
basically, did we do like a transformation to that? Can we like
Yeah.
take it in that manner?
Yes, exactly. Because
Okay.
sine of 2x, that is a transformation that happened to the graph of sine. And so we want to make sure that we include all of our possible values that way.
And if there was a situation where like our final X answer was, let's say, greater than 360, we
Mhm.
wouldn't include that. Like we did that wrong, basically.
Correct. But if that were to happen, that possibly means that you included a original value that you shouldn't have included.
Okay.
Right? And then the other types of problems that we can have that are still amongst like the simpler type are ones like this, where we're trying to solve 2 sine squared x plus 5 sine x minus 3 is equal to 0. And again, we're doing this for 0 to 2 pi. Now, of course, this one, it has x, so we don't have to worry about adjusting our domain. But this problem looks very much like a quadratic. Okay, it's just that instead of it being just a regular x squared and an x, it's a sine x, which means is that I could factor these problems as well. It's just that instead of having an x and an x, we have a sine x instead. So I'll say that again. If you're able to factor a quadratic like this, then you're able to factor a quadratic that has a trig function. It's just instead of having x and x, you're gonna have sine x and sine x instead. So taking it back to California, 2 times -3 is
-6.
factoring. The X method, California X method, slide divide bottoms up. It has so many names. Yes, it has many names. So you multiply your A and your C together to get -6. Now you're looking for 2 numbers that multiply to give you -6, but add together to give you
5.
5. What's
-1, 6.
Okay, so technically this would be A minus 1, A plus 6, but we have to divide both sides by 2.
Slide up the first one to make it 2a minus 1, and then the next one will simplify to a plus 3.
There you go. So that's how this quadratic factors, and that's exactly how 2 sine squared x plus 5x plus 5 sine x minus 3 factors down to b. It'll be a 2 sine x minus 1, and then a sine x plus 3. If I FOIL this out, I will get exactly what I see on the board in purple. So again, using my skills of factoring, I said each factor equal to 0. And I'll continue to solve. For the first one, I'll add over 1, divide both sides by 2. And now I'm looking for where sine is 1/2 from 0 to 2 pi. Again, that's why it's so important that we know how to do our unit circle. We know the angles and radians and degrees and ordered pairs of our unit circle. So where is sine a positive 1/2?
Do we do it in radian terms?
Yep,
Okay. Is it pi over 6, one of them?
yep,
On the full thing?
from 0 to 2 pi, yep. So I have pi over 6, that's one of them. 5 pi over 6, anywhere else?
Um,
No,
Where's-
ma'am.
Nope, okay.
I don't think so.
Yep, that's the only two where they're positive. So that's one set of solutions. This one, when I subtract 3 from both sides, now I'm asking myself, where does sine equal a -3? Does that exist on the unit circle?
No.
Where
No.
one of the y coordinate is -3? No.
No.
So this will be an example of, no solutions for this particular set. So my only answers are these two right here.
It's like a complex problem for a very simple.
Yeah, sure.
So you know how in the past we used to check for, a quadratic like this? So would there be a scenario where we have to check, or will that happen when we're trying to find the values?
Well, we can always check by plugging in our x values into the original equation. You'll just be working with, the ordered pairs and things like that. I would say checking, for like the last little bit, if you got 5 minutes left on the quiz and you want to double check, make sure your answers work, plug in and do that there.
No, like what I mean is like, how when we originally did it, we got answers and all of that, and we think it's the right answer, but when you plug it in, you find out that it's not. Like, will we have a scenario like this?
No,
Okay.
not the ones you'll deal with.
Okay.
The same thing when you know something.
What?
Friday, October.
With this particular question, to solve it, okay, we have our domain, so all of our answers are going to be in what measurement?
Radians?
Radians. And this one, we are going to have to do what to solve it?
Quadratic.
Factor.
It's going to be a quadratic, so we're going to factor. How did this factor down?
Nikki said.
Anyone?
2 sine x plus 1 and sine x plus 1.
Very good. Okay, because it's just like a regular quadratic. Okay, slide divide bottoms up. We get 2 sine x plus 1, sine x plus 1. So we set both factors equal to 0. So here's the first one. Subtract over 1. Divide by 2. And now you're asking yourself, where on the unit circle from 0 to 2 pi does sine equal a -1/2?
7 pi over 6. And
Very good. It's bounded between the third quadrant and the fourth quadrant. So that's very good for those. Now let's do sine x plus 1 is equal to 0. When I solve that, that's going to be sine x is equal to -1. Now I'm asking the same question, except this time where does sine equal a -1?
it's not a thing. Wait, it is.
It was 3 powered.
3 pi over 2. So this one actually, both factors had a set of solutions. 3 pi over 2 was for the one that was between, for a -1, and the 7 pi over 6 and 11 pi over 6 were for where sine was a -1/2.
Where's 3 pi?
So for this particular problem, cosine 2x equal to √3/2. Hopefully you noticed that I am going to have to adjust my domain to what?
-360. X, no, wait, +360.
Exactly, because I have to multiply both sides by 2 to make sure it's 2x. Now this is so I can make sure I include all the possible solutions where cosine is a positive √3/2. That occurs in which quadrants?
The right, top right one.
Top right?
Yes, and the top left.
No,
wait.
now where cosine's positive is the first quadrant and
Bottom
The
right.
last quadrant.
the fourth quadrant. Remember, all students take calculus. All of them are positive. Calculus, cosine's positive.
That's right.
So
Oh, it's a cosine problem.
it's a cosine problem. Mhm. Cosine is X or Y?
X.
It's X. So in the first quadrant, what was that angle as a degree? Because these were degrees.
30.
30 degrees. And then in the fourth quadrant, going from 0 to 360.
330.
Very good. Then what about going in the negative route? Remember, negative is clockwise.
Negative 30.
Negative 30, which would be this angle. And then this one up here.
Negative 330.
Very good. And so that doesn't mean those are my solutions. That means I have to set 30, 330, negative 330, and negative 30 equal to 2x to actually find my final answer. So what's half of 30?
15.
So 15 is one of them. What's half of 330?
165.
And then of course, the negative versions are going to be the exact same, negative 15 degrees and negative 165 degrees. And if you notice, every single one of these lie in between 180 and negative 180, because this is exactly what x equals. But I use the new domain, so then that way I can find all the solutions that would fit this equation.
Yeah.
So in this particular one, we got tangent 3x is equal to 1, where my answers are going to be in degree of radian. Radian. And hopefully you notice as well that I got to adjust my domain. So when I do that, my domain is now going to be from what to what?
Negative 3 pi to 3 pi.
Exactly, because I got to multiply both pi's by a 3, negative and positive. So now I'm asking for where does tangent equal a positive 1? Remember, tangent is what over what?
Sine
Sine over cosine.
So sine over cosine, which is y over x. And so essentially, I need these set of ordered pairs that are going to be the exact same thing to cancel out to be 1. That can only happen if I have a square root 2 over 2 divided by square root 2 over 2. That happens at 45 degrees, or pi over 4, and 5 pi over 4. But I'm going from negative 3 pi to positive 3 pi. So from 0 to 3 pi, I have to go around one more time to reach the positives. So then that's going to be also a 9 pi over 4.
Okay.
Because I'm going around one full time, so that's 2 pi. And then if I add 2 pi and pi over 4, that's going to give me 9 pi over 4. So all of my positive angles are pi over 4, 5 pi over 4, and 9 pi over 4 so far. But now I need to get my negatives, which I get when I go in the clockwise direction. So clockwise, here, this will put me at a negative 3 pi over 4. Keep going. This one will put me at a negative 7 pi over 4. And then if I keep going until I reach a negative 3 pi over 4, then I'm going to be at a negative 11 pi over 4. And those will take care of my negative angles.
I was right, Lucas.
What about what?
That's what I was originally doing. What I was trying to warn you about until you were like, I'm wrong.
But you are though.
But remember, I gotta still set every single one of these equal to 3x because I'm still trying to solve for x. So I need to divide every single one by 3. So my final answers are pi over 12, because pi over 4 divided by 3. Keep change flip is pi over 12. My next one's going to be 5 pi over 12. And then 9 pi over 12, which reduces down to be
3 pi over 4.
Thank you. Then over here, I'm going to have a negative pi over 4, because it would have been negative 3 pi over 12, which reduces down. Then I'm going to have negative 7 pi over 12. And my last answer is going to be negative 11 pi over 12. And every single one of these lie between negative pi and positive pi.
Can you explain again the negative part?
Yes. So remember, when we're going in the clockwise fashion, all of our angles are negative. So this is a negative pi over 2. This is a negative pi, negative 3 pi over 2, negative 2 pi. Keep going. This will then be a negative 5 pi over 2, and then a negative 3 pi once I wrap around again. So if I'm trying to find what this angle is, it's essentially the corresponding value if I was heading counterclockwise, which is 3 pi over 4. But since I'm going in the negative direction, it's negative 3 pi over 4 because it's bigger than 1/2, but less than 1.
Wait, where did you get 3 pi over 4?
Think about it, it's the exact same angles, I'm just heading clockwise. So this is negative pi over 6, negative pi over 4, negative pi over 3. I'm heading essentially the exact same angles, just going in the negative direction. This is negative 2 pi over 3, negative 3 pi over 4, negative 5 pi over 6, negative pi.
Yeah, why is it not negative pi over 4?
Because I've already traveled a pi over 2 radian in the clockwise fashion. Like this angle I'm looking for is right here.
Why?
Can I
Because
try to explain it?
this is the ordered pair that has negative root 2 over 2, negative root 2 over 2. The ordered pairs don't change in the unit circle.
Oh, they don't?
No, they never did.
Oh.
It's only the angles that change, but the ordered pairs are still the same.
Lucas, if you look at the distance, so if you go counterclockwise, you're going to like 2 whole quadrants and then into the 3rd quadrant. So since it's less, since you're just going like a quadrant and basically a half, if you do that in terms of counterclockwise, it would be in the 2nd quadrant. And that's how we get it to be this angle. It's just the negative of where it is at the 2nd quadrant.
Exactly.
I don't understand what that means, so I'm gonna go.
All right, so this one, what did you have to do to solve this?
Factor?
It's a quadratic factor, and it was just like this quadratic, except the difference was that it was cosine and not sine. So
No, there is a minus as well.
oh, okay. But it was still pretty close, right? One was 2 cosine x
Plus 1.
plus 1, and then cosine x minus 3. So when I set these equal to each other, I'll have cosine x equals a negative 1/2. I skipped a few steps on the inside. Is that okay?
Yeah.
And cosine x is equal to 3. So we're on the unit circle from 0 to 2 pi is cosine a negative 1/2. Very good. And where is cosine a 3?
Never.
Never.
Exactly. So my only solutions are these. Very good. For this one, hopefully you recognize that you were going to have to change up your domain. I have a pi over 3.
Oh.
Oh yeah, we forgot about that.
Not a pi over 3, an x over 3. Well, let's adjust it now. That means I have to divide both sides by 3. What's 180 divided by 3?
60.
60. So I'm going from negative 60 to 60. That's actually a very small window. 60 to negative 60 is here and here. So I'm only looking in this area. But let's solve this out some.
Would we have to convert it into tangent by dividing the cosine?
That probably would actually have been the easiest way to do it, to be honest. Because since they're both squared, if I divide both sides by the cosine squared of x over 3.
Yeah, we got that far, but we weren't sure how to simplify the x over 3 and then the x over 3.
But remember, you don't simplify the x over 3 because that's like your argument. That's what you set the angles equal to after you figure out what the angles are. So I essentially need to get rid of the square. How do I get rid of the square?
Wait, how do you get 2?
Cosine over cosine?
Yeah, but why is it only x over 3?
Because it's the same reason why it's sine x over cosine x, why it's just a tangent. Nothing happens to the angle. It's just the three.
Oh, it's the same value.
Mhm.
Do it square root, both
And then you have to remember, whenever you square root, it is,
plus or minus.
so you're looking for where tangent is gonna be a positive or a negative root 3. Positive is gonna take you from 0 to 60. The negative is gonna be from 0 to negative 60. So which angle as a degree is tangent a square root of 3?
Square root of 3/2 and 1/2. Oh, that's the coordinate. Never mind.
You actually want to where your x is 1/2 and your y is square root 3/2. Because remember, tangent is sine over cosine, and that's how we get root 3. So where's the order pair 1/2 square root 3/2?
60 degrees.
60 degrees.
At 60, so then for negative root 3 is going to be negative 60. So that means I set 60 and negative 60 equal to x over 3 to actually get my final answer. So then I multiply both sides by 3, and x is equal to 180 and negative 180. Because again, I multiply both sides by 3. So don't forget to adjust your domain. Don't forget to make sure you're including all the values on your domain. And then of course, to actually set them equal to the argument that's inside of the parentheses. So that way you can actually get your final answers. And so that is the last little bit of the more simple trigonometric equations that involve factoring, adjusting your domain, the simplistic solving like your problem of the day, where you just have to isolate, use your unit circle, isolate, use your unit circle, and so on and so forth.